So believe it or not, we are still on Module 7 with our 6th lecture on this topic, and we're going to talk about different types of aqueous reactions in solution, including acid-base reactions and gas-forming reactions. So let us get started with the next part of this module. Okay, so we know about precipitation reactions. There are two other important classes of reactions that occur in aqueous solution. These are acid-base reactions and gas evolution reactions. In the lab that details chemical reactions, you will also have experienced these two types of reactions as well. An acid-base reaction is also called a neutralization reaction. And that's because an acid reacts with a base. The two actually neutralize each other, which produces water, or in some cases, a weak electrolyte. But what I get is a neutral solution, not something that's acidic or something that's basic. In a gas evolution reaction, a gas is produced, and I can tell it's produced when I see this sort of vigorous bubbling. So in both acid-base and gas evolution reactions, just as in precipitation reactions, the reactions occur when the anion from one reactant combines with the anion or the cation of the other. Many gas evolution reactions are also acid-base reactions. When I have a gas, okay, that was another duplicate. Let's look again at acids and bases and neutralization reactions. According to Arrhenius, an acid is a substance that dissociates in water to produce hydrogen ions, which are H+. So this is my generic acid where A is just some anion. An example of this would be HCl. HCl dissociates to form H+, and then A- is actually equal to Cl-. In water, this H+ immediately reacts with H2O molecules to produce hydronium ions. So the hydronium ions actually react like this, and then what I get is this ion, which is H3O+, indicated here. According to Arrhenius, a base is something where a substance dissociates in water to produce hydroxide ions, or OH-. Usually it's a metal hydroxide, like sodium hydroxide. This is sort of a generic term for whatever cation is produced. The important part is I get this OH-. Now, ammonia is a weak base because it actually also produces OH- in solution. It just actually has to react with water to yield ammonium and hydroxide ions. This is a weak base, so this reaction actually doesn't occur very much to the product side. Most of the ammonia is still present in its NH3 form. Here are some common acids and bases. We know that there are a handful of strong acids and bases like we talked about before, and then anything that's not a member of this group is going to be and HI is missing from here also, is going to be weak, right? Our strong bases are usually, if you notice, these cations are from group 1A and 2A in particular. Ammonia is a weak base. So it's a really good idea to sort of look at these different formulas and sort of get a sense of what an acid is and what it isn't, and what a base is and what it isn't, and then sort of put these together, because we will be looking at neutralization reactions and how I predict those products. Remember, strong acids are and strong bases are strong electrolytes, which means they're pretty much 100% dissociated, or they dissociate or ionize to a very large extent. Whereas weak acids and weak bases are very weak electrolytes. I have some ionization, but I don't have a lot. I have enough ionization where I can conduct a current, but if I wanted to compare sort of the current that's produced, if I run my bulb in that circuit, my bulb would shine really brightly in the presence of the strong electrolytic solution. Whereas if I had these weak electrolytes in solution, it would be a much dimmer glow to that bulb. Acid-base neutralization reactions are also double displacement or double replacement reactions, just like precipitate. What I actually want to do is take the H and the OH together, and then the metal and the anion together. So this ends up being an ionic compound for the most part, which is a salt, and then I get water. So this is H, and then OH forms H2O, which gives me water. And water that's formed is a liquid, so don't forget that's a little bit different. This is generally in solution if it's an aqueous, if it's soluble in water. So here's an example on a molecular level. If I have HCl reacting with sodium hydroxide, what I'm going to get is the salt, which is sodium chloride, and then liquid water. If I look in solution, this is a strong acid, so I don't have any intact HCl molecules. I have H3O plus and Cl minus, and I don't have HCl molecules intact present in the solution. Strong acids are, this is generally 100% dissociated or ionized. My sodium hydroxide is a soluble ionic solid. This is also a strong base. So this again, I just have sodium ions and hydroxide ions present in solution. Now when I react, what I'm going to form is more water in the liquid phase, and then I'm going to have this salt, but it's in solution. So that salt is actually going to be aqueous sodium ions and aqueous chloride ions dissolved up in that solution. Here is another example of my common acids and bases. Again, if I look here, these are those strong acids that I have to remember, because the mantra here is if I'm not strong, I'm weak. So if I'm not on this list here and I'm an acid, I'm going to be a weak acid. And then again, most of my metal hydroxides are going to turn out to be strong bases, and ammonia is going to be that weak base. Again, you need to get a handle on this, because you have to be able to assess whether things are going to be strong electrolytes or weak electrolytes or non-electrolytes. So you have to be able to look at these formulas and decide whether they're acids, they're bases, or they're non-ionizing molecular substances. So you have to have the solubility rules at hand. You have to know this list of strong acids and what an acid is in general, so that you can make those assessments. Here's another example. These are the strong acids that we've been describing. Now I have this sort of molecular model take, but again, if you need to memorize, if you have to, these different reactions or these different strong acids, because if I'm not strong, I'm weak, right? If I'm not on this list and I'm an acid, I'm a weak acid. So let's look at these neutralization reactions. Let's say I wanted to write the molecular, the complete ionic, and the net ionic equations for the reaction of aqueous HBr, which is a strong acid, and aqueous BaOH2, which is a strong base. What I'm going to do is write the chemical formulas of the products, and I need to use proper ionic rules to write the formula for the new salt that forms. I'm going to do this combination. The H and the OH come together, the barium and the ion and the bromide ion come together. I'm going to get water. Remember, barium is 2 plus and Br is -1. So the right formula is a 1:2 ratio. The right formula for barium bromide is BaBr2. The second step, when I want to do this molecular equation, is I want to make sure I balance the equation and predict the solubility of the salt. Barium bromide is going to be aqueous. It is soluble. I'm not going to form a precipitate. I am going to form an aqueous solution of barium 2 plus and bromide minus ions, as well as liquid water. Now this is the molecular equation, because once I balance everything, this is how I would write the equation as if all of these different substances were actual molecules. The complete ionic equation is just like we described before. I'm going to dissociate or ionize the strong acid and any of the soluble ionic compounds. Remember, solid, liquids, and gases are not dissociated. This is a strong acid, so it does ionize to form 2H plus and 2Br. Again, the 2 is coming from the balanced chemical equation. This is a strong base, so it will form Ba2 plus and 2OH minus. It's also an ionic salt that happens to be soluble, or an ionic compound that happens to be soluble. So what I'm forming is liquid water, which stays intact, and then my barium bromide is soluble in water according to the solubility rules. So that is dissociated into barium 2 plus ions and bromide minus ions. Now I'm going to identify the spectator ions, and if I do that, I find out on both sides of this reaction arrow, I have barium 2 plus, and I have 2 bromines. So those are all going to cancel, and what I'm left with is actually 2H plus 2OH gives me 2 H2Os. Now, I have a 2 to 2 to 2 ratio. So if I divide everything by 2, because I always want to have my balanced chemical equation as the lowest whole number ratio, I'm going to get this equation, which is actually the net ionic equation for this acid-base reaction. you're going to find out that this is a common equation in many of your acid-base neutralization reactions, because what happens is the H plus from the acid and the OH minus from the base react to form water. This is the reaction that occurs between those two ions, and this is usually what the net ionic equation is for acid-base reactions. So let's look at another example. I'm going to write the molecular, the ionic, and the net ionic equations for the reaction of aqueous sodium hydroxide and aqueous HF. Now I know this is my strong base, but HF, remember, if I'm not strong, I'm weak, right? So this is a weak acid, which means it is not dissociating very much because it's weak. If I write the formulas of the potential products, I'm going to do the same thing I did before. The H and the OH combine, and then the sodium and the fluoride combine. I'm going to get water and NaF. This will be aqueous. This is a soluble salt, so that will be aqueous, and then I'm forming liquid water as well. So in the molecular equation, I'm going to balance the equation and predict that solubility. According to the solubility rules, this is in fact aqueous, and I have 2 hydrogens on each side, 1 oxygen, 1 sodium, 1 fluorine, so this is actually balanced the way it is written here. So this whole thing is going to be my balanced molecular equation. Here's a tricky part. Remember, this is a weak acid, so it is a weak electrolyte. So in the ionic equation, this is actually the substance that you see. Sodium hydroxide is a strong electrolyte. It's a strong base, so it is completely dissociated. Weak electrolytes in my ionic equations remain intact. I do not ionize or dissociate or do anything. This is going to stay the way it is because it's a weak acid. So knowing those 6 strong acids so you can figure out what's weak is really important in this part of the lecture, because if I don't know that this is a weak acid and that it's not going to dissociate or ionize fully, I'm not going to get this part of the problem right. When I come to the other side, this is an ionic compound, which happens to be soluble. So it's a strong electrolyte, and it will be fully dissociated. And then water is molecular, it's a liquid, it's not dissociated. So this is actually the complete ionic equation. This HF stays intact, and the H2O is going to stay intact as well. Now, when I want to figure out what the net ionic equation is, I'm going to notice, hopefully, that the only spectator ion I have is sodium. I have HF on this side, and I have F minus on the reactants or on the product side, and they don't cancel out. The only thing that cancels out are these sodium ions. Those are the spectator ions in this particular reaction. So if I take those out of the picture, what I get for the net ionic equation is going to be this equation here, which is HF aqueous plus OH minus aqueous, reacting to form H2O liquid plus F minus aqueous. So let's practice. If I want to predict the products of these two acid-base reactions, what I'm going to do is combine the H and the OH and then combine that. So what I'm going to get is H2O liquid plus barium. Now remember, barium is 2 plus, nitrate is -1. So I need 2 nitrates in this formula. I'm going to look at the solubility rules. This is in fact aqueous because it's a nitrate. And then I'm going to check whether I'm balanced. I am not because I have 2 nitrates on the product side and only 1 on the reactant side. So I'm going to put a 2 here. That gives me 2 hydrogens, but notice I also have 2 hydrogens. So on this side, I have 4 hydrogens, which means I'm going to make 2 water molecules. Once I make those 2 changes, I am now completely balanced. If I wanted to make the complete ionic equation, I would do 2H plus aqueous plus 2NO3 minus aqueous. Nitric acid is a strong acid, so it is completely ionized. And then I'm going to get Ba2 plus aqueous plus 2OH minus aqueous goes to 2H2O liquid. That stays intact. This is soluble. So I'm going to get Ba2 plus 2NO3 minus, and I want to make sure I put those aqueous states in there as well. So this is my complete ionic. Now notice, I'm going to identify spectator ions. I have this barium 2 plus on both sides of my reaction arrow, and I have the 2 NO3s on both sides of the reaction arrow. Those are my spectator ions, so I'm just going to get rid of those. And then what I'm left with in terms of my net ionic is 2H plus 2OH minus aqueous goes to 2H2Os. And just like before, I can cancel those. So what I get is H plus aqueous plus OH minus aqueous goes to H2O liquid as my net ionic equation. Let's try this next one. I'll use a different color. I take the H and the OH, and I take the lithium and the sulfate. I'm going to make H2O liquid. The salt is going to be lithium, which is a +1, sulfate, which is a -2. So I get Li2SO4. That's aqueous because it's a group 1 cation. Lithium is a group 1 cation. It's always soluble. Am I balanced? No, because I have 2 lithiums. I need a 2 in front of this lithium hydroxide, and then that changes the amount of hydrogens. So I also need a 2 here in order to fully balance the reaction. So again, I could write the complete ionic and the net ionic equation. And basically for my net ionic equation, I'm going to get the same thing as I got here. My spectator ions are going to be the lithium plus ion and the sulfate 2 minus ion in this particular case. Now, we're going to quickly cover titration. Titration is a technique that's really important in a chemistry lab because it's an analytical technique. What it is a procedure to determine the concentration of a solution. So this is an unknown. I'm going to allow a measured volume of that solution to react with a second solution of some other substance. This is called the standard solution. And this substance has a concentration that is known. So, for example, I could figure out an unknown solution of HCl by titrating it with a known concentration of a sodium hydroxide solution, and then figure out that once the reaction is complete, I'm going to be able to calculate the concentration of that unknown solution because of stoichiometry. If I know how many moles of NaOH react with my unknown amount of HCl, I can figure out the moles of that HCl, and if I have that measured volume, molarity equals moles over volume, I can calculate that concentration of my unknown solution. So how can you tell when the reaction is complete? Acid-base reactions actually give a soluble salt generally and water. So none of those is something that's visible. So basically, I have to use an indicator. An indicator is something that is going to change color when I change the pH. So if I have a measured volume of acid solution that I put in a flask and I add an indicator, when I add my base solution of known concentration, I'm going to use a burette until I get a color change. When I read the volume of the base from the burette, I will have molarity of the base, and I will have the volume of the base, which allows me to calculate the moles of the base. This is a known concentration or a known amount. So to calculate the molarity of the unknown, right, if I have moles of the base, I can use stoichiometry to get moles of the acid. All I have to do is look at the equation, and then I'm going to get moles of acid over the amount of unknown in liters, and that'll allow me to calculate the molarity of that unknown solution. Now, it's really unfortunate that we're not going to be in the lab to do this. I do have a simulation for this particular reaction, but it's just not the same. And usually in class, we have a sort of a competition to see who can get the best endpoint. This endpoint, you want to be have a very, very, very faint pink color. When I use phenolphthalein as the indicator, I get this pink color change, and that endpoint, to be perfectly precise and accurate, is going to be a very subtle color change. So let's go over some terms. Titration is an analytical method to determine the concentration of a solute in a sample by reacting it with a standard solution, or a solution that I know stuff about. So my standard solution is a solution of known concentration. It's also called the titrant. The equivalence point is the point when the moles of added titrant, when the moles of that standard solution are stoichiometrically equivalent to the moles of the substance being analyzed. This is my end point, and this point is reached when my indicator actually changes color. There are many different indicators, and I can choose the indicator based on the pH range where the color change actually occurs. When you take Chem 2, you're going to learn a lot more about acid-base reactions. We're focusing on one type, which is a strong acid with a strong base. So my endpoint is a little bit easier to understand. So let's do an example problem. Let's say I have 48.6 milliliter of my known 0.100 molar sodium hydroxide solution. The volume of my unknown is 20 mils. I want to figure out the concentration of this unknown HCl solution. Basically, I'm going to do solution stoichiometry. I'm going to write the equation of the acid and the base neutralization reaction. So if I do that, this actually is not a 2 there. I have a 1-to-1-to-1-to-1 relationship. So by knowing the volume of the sodium hydroxide and the molarity, remember that allows me to calculate moles of sodium hydroxide. I can use the balanced chemical equation to figure out that stoichiometric mole ratio between the two reactants. That allows me to convert to moles of the unknown substance. And then I know the volume that I put in. It was at 20 mils. And I can calculate using the moles and the volume of HCl that molarity of the unknown concentration. So I can use this titration procedure to figure that out. So let's do the calculation. If I start with 48.6 milliliters of sodium hydroxide, I do want to convert that to liters so that I'm in moles. This is the molarity of my NaOH solution used as a conversion factor. So if I do this calculation, this is the amount of moles of sodium hydroxide. Well, the stoichiometry for this reaction is 1-to-1. So if this many moles react, remember, this is from the burette reading. It used this 48.6 milliliters to actually react with all of the acid that was available. So I also just calculated the moles of HCl that were in that solution. So this many moles were in of HCl are in the amount of HCl we titrated. So I can convert my volume of solution to milliliters, and then I can calculate my molarity, which is moles over liter. And what I find out using this technique is that my unknown HCl is 0.243 molar. So let's practice. I have sulfuric acid, and I have my known volume reacting with 18.45 mils of sodium hydroxide. I want to write the reaction out of this acid and this base. So I want to write the neutralization reaction. Sulfuric acid is H2SO4 plus sodium hydroxide goes to water plus the salt, which is sodium sulfate. And that is aqueous because it's a sodium salt. Notice this is not balanced. I have a 2 here because I have 2 sodiums on the product side. And now I have 4 hydrogens on the reactant side. So I'm actually making 2 molecules of water. So this is a 1-to-2 stoichiometric relationship. I know the volume and the molarity of my sodium hydroxide. So my moles of NaOH is going to equal to 0.0973 moles per liter, I'm going to convert this to liters, which is 0.01845 liters. So that's my volume. So 0.01845 liters. That cancels. What I get here is going to be 0.0973 times 0.01845. What I get is 1.80 times 10 to the minus third moles of NaOH. Well, now it's going to be a solution stoichiometry problem. If I have 1.80 times 10 to the minus 3 moles of NaOH, to convert that into moles of H2SO4, I know for every 1 mole of NaOH, or every 2 moles of NaOH, I react with 1 mole of H2SO4. So this is going to give me moles of H2SO4. So I take my moles and I divide by 2, and I get 8.98 times 10 to the minus 4th moles of H2SO4. Well, remember I had that volume of 15 mils of H2SO4, which also is 0.01500 liters of H2SO4. My molarity of my H2SO4 is going to equal to 8.98 times 10 to the minus 4th moles of H2SO4 divided by 0.01500 liters. Remember, moles over liters. And what I get is a molarity of 0.0598 molar. Hopefully I did all my math right. And if not, maybe you guys will catch it. So this is the unknown concentration of the H2SO4. This one I'm not going to do because basically it's a 1-to-1 ratio, which is a little bit easier. Do this one, try this. It's very similar to the example calculation. The other thing I want to say about this section is there are going to be a couple of gas evolving reactions that you are required to know. So let's go over those. Sometimes if I do my ion exchange, my double displacement, what I get is a gas that forms directly. So this sulfide reacts with an acid to form H2S, hydrogen sulfide. This is actually produced directly from this ion exchange, and this is going to bubble up as my gas. Other reactions will form a gas by the subsequent decomposition of one of the ion exchange products. So here I have sodium and chloride, and then my other ion combination is going to be the H from the HCl and then the sodium or the bicarbonate. That gives me this, which is carbonic acid. Carbonic acid is going to spontaneously decompose to produce water and carbon dioxide. So the actual product of this reaction is this, because this is going to go ahead and react to form the water and the water and carbon dioxide. So this is bicarbonates and carbonates will typically react with acids to form carbon dioxide water, and then whatever salt those ions form. So this is what you might see. When I take sodium bicarbonate and I react it with HCl, again, I'm getting CO2 gas evolved. So you're gonna notice I have all this bubbling or effervescence. It's kind of the plop, plop, fizz, fizz Alka-Seltzer. And within those bubbles, what I have is the carbon dioxide gas, which is going to rise up in the solution, right? And then diffuse away. So these are the reactions you need to know. This is a table from our book. Sulfides will produce H2S when they react with acids. Notice most of these are reacting with acids in order to form these gases. Carbonates and bicarbonates will form CO2 because I have that breakdown of the carbonic acid that's formed, the H2CO3. Sulfites and bisulfites will also break down. This is the intermediate product. And then what I get is SO2 and water. So these are very similar because I have this ion exchange which gives me those products, and then they're gonna further decompose. And notice that this is very similar in this reaction. I form water and carbon dioxide with carbonates and bicarbonates, and I form water and sulfur dioxide with sulfates and bisulfates. Now, when I have ammonium, like a lot of times I'll have an intermediate product of ammonium hydroxide, which again is going to give off ammonia gas plus liquid water. So the gas evolved here is ammonia. Again, I do this double displacement and I end up with ammonium hydroxide, which then is going to break down to these, to these guys. And that's the other gas evolving reaction that I'm going to know. So at this point, we're done with this section, and we have one more section, and then we will finish with Module 7. So have a nice night, and I'll see you soon.